Triple integrals. Just like we have done in the past for single and double integrals, let's start with the geometric motivation for the triple integral. We start with a solid G in three-dimensional space. Here we're thinking of G as the domain of some function, W equals f of x, y, z of three variables. We begin by placing that solid in a rectangular box and then chopping up that box into n sub-boxes. For each of these boxes, we choose a point ck, dk, ek in that box that is part of the solid G whenever possible. Some of those boxes could not contain the solid. If that's the case, we just ignore those boxes. We then evaluate the function at this point ck, dk, ek. So we see here we take f of ck, dk, ek. We multiply that by delta v sub k, which is the volume of the box that we found that point in. We then add up all of those computations. We take the sum as k goes from 1 to n of f of ck, dk, ek times delta vk. And then we take the limit of this process as n goes to infinity. And we call this the triple integral over g, f of x, y, z, dv. And you can see the notation for that on the left there. Just like with double integrals, the way that we actually will compute triple integrals is by doing an iterated integral. We can do the iterated integral in one of two ways. We could iterate it into three integrals right away, or we could leave it as a double integral of a single integral. Depends on the particular problem we're doing, which of these is easier, but you could do it either of those two ways at any time. Let's start with a simple example of a triple integral over a rectangular box. This is handled in exactly the same way you would do a double integral over a rectangle. So why don't you go ahead and pause the video, try this example yourself, and then resume the video to check your answer against mine. Okay, so evaluate the triple integral over the solid G, 2x squared y cubed z dv over this given rectangular box. Note that in this problem, even though we don't spell out what G is, it's implied that G is the rectangular box given there, where x is between 0 and 3, y is between 0 and 2, and z is between 0 and 1. Here's a picture of that box. So we start by changing the triple integral into this iterated integral. Notice that x is going from 0 to 3, y is going from 0 to 2, and z is going from 0 to 1. Notice in this case that all of the limits on the integral are constant, and the integrand is a function which is a product of a function of x, a function of y, and a function of z. Whenever we have this situation, we could actually just rewrite this as a product of three separate integrals. So first of all, I pulled out the constant 2, and now I just did the x integral, which is x squared, so that becomes x cubed over 3, and that's going from 0 to 3. Then I did the y integral, which is y cubed. That becomes y to the 4th over 4 from 0 to 2. And then finally the z integral, that's just z, so that becomes z squared over 2 from 0 to 1. Once again, this little shortcut can only be done when all of the limits are constant and the function inside of the integrals is a product of functions of x, y, and z. An example of a function where you wouldn't be able to do this would be something like the sine of x plus y plus z. That is not a product of functions of x, y, and z, so it wouldn't work in that case. In this case, we could do this little shortcut. If you don't do the shortcut, that's okay. You could just do one integral at a time as well. It'll just take a little longer. But here we employed that shortcut, and now we just go ahead and plug in the numbers. For the x, we just need to plug in the 3, and we get 3 cubed over 3, which is 9. For the y, we just need to plug in the 2. We get 2 to the 4th, which is 16 over 4 is 4. And for the z, we plug in the 1. We get 1 squared over 2, which is 1/2. So we have 2 times 9 times 4 times 1/2, which is 36. Now, the solids that we use obviously will not need to be rectangular boxes. So we're going to focus on a particularly simple type of solid called a simple XY solid. A simple XY solid looks like this. It's a solid that's above a region R in the xy plane, and it goes between two functions of x and y. So notice on the bottom there, we have one surface, that's the graph of z equals g1 of xy, and above that we have another surface, which is the graph of z equals g sub 2 of xy, and the solid that we're looking at is above that region and between those two surfaces. That's called a simple xy solid. And we could compute this type of triple integral as follows. We change the triple integral into a double integral by taking the double integral over the region. And then the inner integral becomes the integral from g1 of xy to g2 of xy of f of xyz dz. And notice that that is the double integral over r of whatever that turns out to be dA. So as I said earlier, we could change the triple integral to a double integral of an integral. And then we have two choices. We could either evaluate that inner integral first and then just do the corresponding double integral, or we could go ahead and change this to an iterated integral involving three integrals. I also just want to mention that just like a simple xy solid, we also have simple xz solids and simple yz solids. The simple xy solid, notice, is oriented along the z-axis. A simple xz solid would be oriented along the y-axis, and a simple yz solid would be oriented along the x-axis. And we would handle those types of integrals in an analogous way to the way that we do this type. I also just want to mention that just like for a double integral, if you put nothing inside of the double integral, you get the area of the region. If you take the triple integral over g dv with nothing inside, again, meaning there's a hidden 1 inside, then that computation will give you the volume of the solid G. Okay, let's go ahead and try an example that is a simple XY solid. Go ahead and pause the video, try this example yourself, and then resume the video to check your answer with mine. Find the volume of the solid within the cylinder, x squared plus y squared equals 9, and between the planes z equals 1 and x plus z equals 5. As usual, the first thing we want to do is get a sketch of this situation so that we could label the limits on our integral properly. I'll start by drawing this cylinder. X squared plus y squared equals 9 is a cylinder of radius 3 with the z-axis running through its center. The plane z equals 1 is a plane parallel to the xy plane and 1 unit above it. The plane x plus z equals 5 looks something like this. Notice how the plane slices the cylinder diagonally. If you want, you could picture a can of soda and what would happen if you cut that can of soda diagonally downwards. You would get something that looks a little like this. I also rewrote the equation x plus z equals 5 as z equals 5 minus x, so that in this picture we could clearly see what the z limits are going to be. The lower z limit is the function z equals 1, and the upper z limit is the function z equals 5 minus x. Also, we're interested in the region. The region that we're going to be integrating over is this circular region in the xy plane. That's just a circle of radius 3. So as mentioned, since this is a simple xy solid, we can change the triple integral to the double integral over r of the integral from 1 to 5 minus x dz times dA. So that inner integral becomes z from 1 to 5 minus x, which is 5 minus x minus 1, or 4 minus x. Now we have to do that double integral. The best way to do that double integral is by using polar, because the region is a circular disk. So in polar, we see that theta is going from 0 to 2 pi, and r is going from 0 to 3. We replace the x in the integrand by r cosine theta, and don't forget to multiply by that extra factor of r because we're doing this in polar. So distributing that r through gives us 4r minus r squared cosine theta. So I'm just going to split this integral into two pieces, the double integral of 4r dr d theta minus the double integral of r squared cosine theta dr d theta. Once again, just like in the last example, each of these double integrals has the property that all of the limits are constant, and the function in the integrand is a product of a function of r with a function of theta. For the leftmost one, it's 4r times 1, we could think of it as. So we just have the integral from 0 to 3 4r dr times the integral from 0 to 2 pi 1 d theta, or just the integral from 0 to 2 pi d theta. For the rightmost integral, we could write that as the product of the integral from 0 to 2 pi cosine theta d theta times the integral from 0 to 3 r squared dr. Okay, so that first integral, the integral from 0 to 2 pi d theta, is just 2 pi. The integral from 0 to 3, 4r dr, that becomes 4r squared over 2 from 0 to 3. The cosine theta becomes a sine theta when we integrate, and the r squared becomes r cubed over 3 when we integrate. Sine theta goes away because the sine of 0 and the sine of 2 pi are both 0, so anything times 0 is 0, so that whole right-hand side is just 0. So we just have to do the left, and when we plug in a 3 for r, we get 9 times 4, which is 36. The 2's cancel, and we wind up with 36 pi. Let's do one more example. This one is a little tougher. So you might want to do this in 2 steps. First, see if you could set up the integral properly, and then go ahead and see if you could actually compute it. Both of those parts are a little more challenging than anything we've done so far. So don't worry if you have trouble with it. Do the best you can. Then after you pause the video and try it, resume the video and follow all of my steps carefully. Find the volume of the solid enclosed between the paraboloids z equals 5x squared plus 5y squared and z equals 6 minus 7x squared minus y squared. As usual, we're going to want to sketch this solid first. So let's draw the first paraboloid first, z equals 5x squared plus 5y squared. That's an upward facing paraboloid with vertex at the origin. The second paraboloid, because it's negative 7x squared minus y squared, it's upside down. And the 6 tells us to shift it upward 6 units. So it looks something like this. The solid enclosed between the paraboloids is this yellow solid region here. And the intersection of those 2 paraboloids is this little ellipse over here. Yeah, I'm just going to make this picture a little smaller so I have some room to work. First, I want to find the equation of that ellipse. I can do that by solving the system of equations defined by those 2 paraboloids simultaneously. So since each of them is solved for z, we could just set 5x squared plus 5y squared equal to 6 minus 7x squared minus y squared. And bringing the 7x squared and y squared over to the left, we get 12x squared plus 6y squared equals 6. Dividing by 6, we get 2x squared plus y squared is equal to 1. And that's the equation of that little ellipse. That is the intersection of those 2 paraboloids. I'm just going to draw the projection of that same ellipse into the xy plane, because that is the region that we're going to be doing our integral over. Remember that the standard form of an equation of ellipse is x minus h squared over a squared plus y minus k squared over b squared equals 1. So we see that putting the equation of the ellipse into a more precise standard form, we could rewrite the 2 in the denominator under the x squared as 1/2, and we could place a 1 under the y squared so that we could see clearly that a is equal to 1 over root 2 and b is equal to 1. This gives us a quick sketch of the ellipse as shown here. Notice the ellipse is centered at the origin. We go left and right 1 over root 2 units to get to the vertices on the x-axis, and we go up and down 1 unit to get to the vertices on the y-axis. We're now ready to change our triple integral into a double integral, and in fact, I'm just going to go right to the full iterated integral here because the region is pretty clear there. Let's look at this from the inside out. For the dz integral, we're going from the lower paraboloid to the upper one. The lower one is the green one, which is 5x squared plus 5y squared, and the upper one is the purple one, which is 6 minus 7x squared minus y squared. For the dy and dx limits, we look at that ellipse. I'm going to do it as a type 1 region. So as a type 1 region, x is going from negative 1 over root 2 to 1 over root 2. And y is going from the lower half of the ellipse to the upper half of the ellipse. To see what that is, we need to solve the equation of the ellipse for y. And we see that's y squared equals 1 minus 2x squared, or y equals plus or minus the square root of 1 minus 2x squared. So the lower part of the ellipse has equation y equals negative root 1 minus 2x squared. And the higher portion of the ellipse has equation y equals root 1 minus 2x squared. Also, I just want to mention that since we're finding the volume of the solid, that means that f of x, y, z, the integrand, is just 1. And that's why nothing appears inside of that triple integral. So that's the whole setup. Now we're ready to do the computation. We start by doing the innermost integral, which just becomes z from the lower to the upper limit, which means we just subtract 6 minus 7x squared minus y squared minus 5x squared plus 5y squared, and we get 6 minus 12x squared minus 6y squared. That takes care of the inner integral. Now we want to do the dy integral. So 6 minus 12x squared is constant with respect to y. So that just becomes 6 minus 12x squared times y, which I wrote in a more factored form as 6 times 1 minus 2x squared times y. And 6y squared becomes 6y cubed over 3, or 2y cubed. So that's where that minus 2y cubed comes from. And it's going from the lower limit to the upper limit, from negative root 1 minus 2x squared up to root 1 minus 2x squared. So plugging in those limits, let's see what happens. We have 6 times 1 minus 2x squared times root 1 minus 2x squared, and that gives us 6 times 1 minus 2x squared to the 3 halves. And then we have minus 2 times root 1 minus 2x squared cubed, which again is the same as root 1 minus 2x squared to the 3 halves. So we have 6 of them minus 2 of them. That gives 4 times 1 minus 2x squared to the 3 halves. And since y and y cubed are both odd powers, substituting in the negative root 1 minus 2x squared will give the same thing but opposite in sign. And since we're subtracting, it's just going to double our answer. Since substituting in the upper limit gave us 4 1 minus 2x squared to the 3 halves, the lower limit will also give us another 4 1 minus 2x squared to the 3 halves. So we get a total of 8 times 1 minus 2x squared to the 3 halves. If you're having trouble seeing how I came to that final integral there, go ahead and sit down and make sure you write out all the details yourself. This is just basic algebra, nothing more. Now we're ready to do the dx integral. Unfortunately, this one looks like it's going to require a trig substitution. So let's go ahead and do that substitution. Here's the way I like to do it. I like to start by drawing a right triangle and labeling one of the angles with theta. I then label the triangle with 3 pieces. One is the square root of the expression that is causing the issue, which here is the square root of 1 minus 2x squared. And then I take the square root of each of the terms inside of that square root. So one of the terms is 1 and one is 2x squared. So the square root of 1 is just 1, and the square root of 2x squared is root 2 times x. I label the other 2 sides of the triangle with those 2 expressions, 1 and root 2x. Now, how do I know that I have the sides of the triangle labeled properly? Well, to check, you could just do the Pythagorean theorem. Notice that when we square the 2 legs and add them, we get 1 minus 2x squared plus 2x squared, which is in fact equal to 1. So the Pythagorean theorem works, and that triangle is labeled properly. If the Pythagorean theorem failed, we would know that we would need to interchange some of those expressions. And usually it's pretty clear how to do that once you see the equation that you have attempted to write. Now we want to pick a trig function that avoids the messy side here being square root of 1 minus 2x squared. In this case, sine is a nice choice because the sine of theta is opposite over hypotenuse, which is root 2 times x over 1, or just root 2 times x. Solving for x, we have x equals 1 over root 2 sine theta, and dx is 1 over root 2 times cosine theta d theta. Now, it's also worth noticing that the cosine of theta is adjacent over hypotenuse, which is the square root of 1 minus 2x squared over 1, or just the square root of 1 minus 2x squared. This allows us to make the trig substitution quite easily. Notice that in place of 1 minus 2x squared to the 3 halves, I use the fact that cosine theta is the square root of 1 minus 2x squared to get cosine theta cubed, or cosine cubed theta. And also dx is just 1 over root 2 times cosine theta d theta. I pulled the 8 outside of the integral because it's just a constant. Now, what about the limits? Well, when x is 1 over root 2, notice that we get sine theta is equal to root 2 times 1 over root 2, or just 1, so theta is pi over 2. Similarly, when x is negative 1 over root 2, the sine of theta is negative 1, so theta is negative pi over 2. Just simplifying this expression a bit, we get 8 over root 2, pulling out the constant root 2 in the denominator, and cosine cubed theta times cosine theta is cosine to the 4th theta. We could rewrite cosine 4th theta as cosine square theta squared. We're now going to need to use the power reducing formula for cosine. Cosine squared theta could be rewritten as 1/2 times 1 plus cosine 2 theta. So since we're squaring that, we get 1/4, 1 plus cosine 2 theta squared. Pulling out the 1/4 and multiplying it by the 8, we get 2. So we have 2 over root 2, the integral from negative pi over 2 to pi over 2. And I'm just going to multiply 1 plus cosine 2 theta by itself to get 1 plus cosine 2 theta plus cosine 2 theta, or 2 cosine 2 theta, plus cosine squared 2 theta. Now we need to do the power reducing formula one more time on that cosine squared 2 theta to get 1/2 1 plus cosine 4 theta. We're now ready to integrate. 1 becomes theta. 2 cosine 2 theta becomes sine 2 theta. Notice there's a little substitution there. U equals 2 theta. Du is 2 d theta. That's why the 2 went away. And then we have plus 1/2. That's just a constant. 1 becomes theta. And cosine 4 theta becomes 1/4 sine 4 theta. Again, a little substitution there of u equals 4 theta generates that 1/4. And this is going from negative pi over 2 to pi over 2. Now, sine of 2 times pi over 2 is just the sine of pi, which is 0. And similarly, the sine of negative pi is 0. And also sine of 4 theta, that's going to be a multiple of pi as well. So that's going to come out to 0. So we just have to worry about those thetas that appear there. So we have 2 root 2 times theta plus 1/2 theta, which is 3 halves theta. And substituting in the pi over 2, we get pi over 2 minus pi over 2, or pi over 2 plus pi over 2, which is pi. So we just get 3 pi over root 2 after canceling the 2 in the numerator with the 2 in the denominator.